Hello there, and thank you for taking in this session of the Eaves Council of Canada's 2020 Technical Series. In this segment, we'll be introducing you to an analysis on the cost of building enclosures. This is part one of a three-part series looking into the comparative life cycle analysis completed by RDH. Principal author was Dr. Randy Van Straten. Peer review and stewardship was provided by Dr. Ted Kessick, John Garvin, President of the Eaves Council of Canada, and me, Peter Collier, on behalf of its technical committee. A quick observation of our standard copyright and disclaimer notices before moving on. And let's get started. The series is broken down into three main sections. This introductory session will look at the study's basic framework and terminology. Part 2 explores energy codes and related construction requirements, thermal modeling, and energy use. Part 3, we pull the information together starting with our upfront construction costs, life cycle cost comparisons, and the study's conclusions. As with any session or series, it's important that the terminology used is understood in the same way by all of the participants. With that in mind, let's have a look at the terminology used in this video series and throughout the study. Beginning with our most basic terms and then moving on to the more nuanced, let's have a look at R value. If you were to search out a definition online, it may read something like a quantitative measure of an assembly or material's resistance to heat flow at a unit temperature difference over a unit area. Practically speaking, heat energy travels from hot to cold. When migrating through a material, this process is conductive heat loss. As an assembly's resistance to heat flow, or its R value, increases, the lower the rate of conductive heat loss. With this in mind, let's have a look at our other terms. Nominal R value is simply the R value rating of the insulation product in its installed condition. Contribution by other materials is ignored. Clear wall R value accounts for the thermal resistance of the assembly's layers. It also includes for the two-dimensional effect of standard repetitive framing, studs and tracks. Minimum clear wall R values are currently the common metric found in our energy codes. U factor, or U value, where used in the National Energy Code for buildings, is a weighted calculation that accounts for thermal bridging by elements representing greater than 2% of the wall's cross-sectional area. It is the inverse, if you will, of the the clear wall R value definition. Thermal bridging is assigned to a material with a higher thermal conductivity, that is, it allows heat to travel through it more readily, than the surrounding material in which it spans. A common example of this would be a steel stud in an insulated wall assembly. If we look at a steel stud within a heating environment, that is a warm interior and a cold exterior, the stud's flange is a very effective collector of heat energy. This heat energy is conducted across the stud's webbing, our bridge, where, in the absence of anything to resist its ongoing migration, this heat energy is lost to the exterior, i.e. heat energy loss. Of course, the antidote to this sort of heat loss is continuous insulation. At the risk of oversimplification, continuous insulation reduces the effects of thermal bridging by adding insulated distance between the exterior and interior environments. This effectively reduces the temperature difference across the conducting material that spans a wall assembly and helps to mitigate heat energy loss. Mechanical attachment loss is simply the loss of heat energy through the things used to anchor the cladding to the supporting structure. Whole wall R value accounts for all the things I've described so far, plus a couple other items we'll look at in a moment. Whole wall R value is sometimes referred to as effective R value, as it's the measure of an envelope's effectiveness once all other factors are considered. High R is the term that we use to define assemblies designed to provide a whole wall R value of 40, or an RSI value of 7 in metric units. For thermal linear transmittance, the study uses the ISO 7345 definition, which, to simplify, accounts for the thermal conductivity of a material or building element over its length. When psi is used to characterize linear thermal bridges in the building envelope, it's not the total but the additional heat transfer through the thermal bridge. Point thermal transmittance is again a measure of a material's thermal conductivity transferring heat energy through an assembly. Examples are mechanical system penetrations or structural support elements that have limited spans and would be more accurately accounted for as a point element as opposed to a linear one. Window flanking loss are losses around the window, and those losses are in addition to those captured by our clear wall R-value calculation. It doesn't include the U-value of the window itself. It may be helpful to think of window flanking as a hole in the building's envelope, allowing heat to leak. The greater the gap between the window and the plane of thermal resistance, the greater the potential for heat energy loss. Wrapping insulation into the window's return aids in thermal preservation. For the purpose of this study, and in our modeling, all window conditions were modeled with insulated returns to mitigate window flanking loss. Floor-to-wall losses are losses related to floor assemblies penetrating our exterior wall assembly. These losses may also include for items such as through-wall flashings and cladding mounting systems, i.e. shelf angles and masonries that are located at these interfaces. Without exception, all of the assemblies included in the study utilized a continuous insulation, including at floor lines. Some assemblies, however, have greater potential for thermal bridging at this location, simply due to the methods and means of construction. Where possible, beyond typical construction practices were used at these locations to minimize those effects. For example, for masonry assemblies, offset shelf angles and lintels were used. Looking now at the language of the cost study, life cycle cost analysis is a technique of economic evaluation that sums up the costs of an investment decision over a given study period and is expressed in present or annual value terms. It includes the cost of the initial investment, replacements if and when required, operations including energy use, maintenance, and repair. Initial cost, we look at the definition found in ASTM E631, which includes for a broad range of project delivery related costs, well beyond the costs of the materials themselves. For this study, RDH enlisted the leading cost consultants at Finnegan Marshall. Energy costs capture the energy use costs related to the building operation and, for our study's comparative purposes, relatable to the impacts of the opaque wall system's thermal performance. We'll dig into this in more detail in part 2 of this video series. For maintenance and repair costs, again, we refer to ASTM E631 for methodology, which means that the buildings were maintained at a high level for both structural and aesthetic integrity over a 50-year study period. Present value, sometimes referred to as net present value, includes the initial costs, annual energy costs, wall system repair and maintenance costs over our 50-year study period. In terms of interest rates and escalation rates utilized over a 50-year period, we'll get into that in more detail in part 3 of the analysis. Suffice to say for now that the formulary utilized is from ASTM E917. Turning now to our process and learning objectives, I think it's fair comment to say that this study is unique in that it compares both initial and life cycle costs for assemblies designed and constructed to provide the same whole wall R value. As demonstrated in previous studies, if we were to simply use like amounts of insulation, most assemblies do not achieve the same whole wall R value as an eaves-clad wall. For this study, where an assembly's whole wall R value was impacted by things such as thermal bridging, mechanical attachment losses, and the like, construction methods were enhanced and, as required, additional amounts of insulation incorporated so that all of the assemblies reached the same whole wall R value target as established by our eaves wall. This allows for a true apple-to-apples comparison of the various assemblies, designed to deliver equivalent performance of an eaves wall in our various study locations and on our 2 buildings, while also conforming to applicable energy code requirements. As way of background, this is the process that the Eaves Council followed in charting the course for this study. Number 1 was to determine the study's objectives. What did the Eaves Council want to learn through completion of this study? Step 2, determine the cladding alternatives. What alternative enclosure systems are commonly used in Canada and on what building types? 3 was to determine the building locations, what cities provide for the greatest cross-section of climate zones, as well as construction practices. Step 4 was to determine the study period. How many years should be considered for the life cycle costing? The learning objectives? First, information for architects, builders, and municipalities on the comparative performance of eaves relative to other cladding options over a 50-year service life. Then, thermal performance calculations and methodologies that can be used by designers and energy modelers, as well as service life data for cladding systems for use in future environmental life cycle analyses and reportings. Wall type selection was based on frequency of use. Because some alternatives are used more frequently than others depending on the building type, it became necessary to divide the study into two categories: multi-unit residential and commercial buildings. We'll get into the actual construction details in part 2 of this video series. For now, I'll just introduce you to the basic wall types. Of course, we have exterior insulation and finish systems, or EIFS. Our brick veneer wall, that is used in both the residential building and the commercial property. Our fiber cement cladding is our third alternative used in the residential portion of the study. Moving now to the commercial context, we have architectural precast panels. These are large format precast panels providing all of the control functions as well as structural supports. Aluminum composite panels represents our fourth alternative in the commercial context. With regard to what cities to examine, the study looks at 4 locations across Canada. Locations were selected to provide a cross-section of energy codes from the traditional to the more progressive, a spectrum of climate zones, 4 through 7A, as well as accounting for any differences in construction and operating costs. Beginning on the west with Vancouver, applicable energy code, the 2019 Vancouver Building Bylaw. Then moving to Toronto, for a residential building, we look to the Toronto Green Building Standard, SB10 and the National Energy Code for buildings for our commercial property. In Montreal, the Quebec Construction Code rules the day, and in Calgary, our National Energy Code for buildings 2017 edition. As previously mentioned, we're looking at a 50-year study period. A 50-year period was selected to correspond with the 2019 update to the CSA S478 Durability in Buildings Standard. So our basic framework looks like this. We have our building archetypes, a 12-story commercial and a 6-story wood frame, our wall assemblies designed to meet current code requirements, as well as our high R wall in both residential and commercial contexts, and then looking at our enclosure systems on the commercial side, precast, aluminum composite panels, exterior insulation and finish systems, and brick veneer. On the wood frame residential building, again, we have exterior insulation and finish systems, brick veneer, and fiber cement panels. So the process to determine construction requirements and compliance with respective energy codes that RDH followed looks something like this. Step 1 was to determine the continuous insulation needed for the east wall assembly in each city for each building archetype to comply with the applicable energy code. Once that was modeled and the whole wall R value understood, they could then determine the continuous insulation needed for the other wall assemblies to achieve the same whole wall R value as the east assembly for that particular city on the particular building type. Number 3 was then to determine the continuous insulation needed for our high R wall performance. That is our high R wall performance of no less than 40. Some expanded detail on that. So for those wondering how an R40 was selected as the high R value for the high R walls, the rationale in the report looks something like this. It's a simple round number, and it's within the range of some recent studies. I'm sure you can find those online if you were to search R40 and let's say John Straub. An effective whole wall R value can be achieved without drastic changes for most wall assemblies being considered, although it did bring about some constructability challenges for some of the assemblies and therefore represented the responsible upper limit. Going the other way, let us say down to an R30 as an alternative, was too close to some current energy code requirements for some cities within the study. Calgary, for example, is very close to requiring an R30 as it sits right now. So wrapping things up now in this segment of the video series, we have our 4 locations, Vancouver, Calgary, Toronto, and Montreal, as well as our high R wall system. For each location, we looked at the continuous insulation thicknesses required to conform to the applicable code requirement for each location on each building type. That assembly was then modeled to establish our target whole wall R value that was then applied to all of the alternative claddings. So beginning with the eaves, we applied the required continuous insulation to meet the applicable code requirement as well as achieve our high R target value of R40, then modeled to establish a whole wall target that would then be applied to the alternative claddings. So that wraps up this part of the video series. I hope you'll join me on part 2, where we'll look at energy codes and construction requirements, as well as the thermal modeling for our building types, our 6-story wood frame and our 12-story commercial building. We'll look at energy use and corresponding analyses. Part 3, we begin adding all of the inputs together, looking at repairs and maintenance and related costs over a 50-year service life. And that all comes together in our life cycle cost analysis. Well, that wraps up this session of the video series. I hope you found it informative, and I hope you'll join us in parts 1 and 2. Thanks for watching, and see you next time.